Welcome, everybody. Thank you so much for joining us for this installment of our weekly astrophysics seminar at the Institute of Astrophysics of 4th. Today, it is our distinct pleasure to have with us, even though remotely, hopefully in person on the first opportunity once the pandemic is over, Manos Zapartas. Manos finished his undergraduate degree at the Aristotle University of Thessaloniki, like many of us here in Crete. And then he moved to the University of Amsterdam, where he did both his master's and his PhD studies. And after that, he moved to Geneva, to the University of Geneva, with a scholarship from the Swiss government, an excellent scholarship for postdoctoral research, where he's working with the group of Tassos Frangos, who's also very well known to us. And today he will be talking to us about deaths of massive stars in binary systems. So already the dragon is setting the bar very high. We're very excited to hear about that. Without any further ado, Mano, you have the floor.
Thank you very much for this introduction, and thank you very much in general for the invitation to give this presentation. I'm very happy to do it. Of course, I would prefer to do it that we are all together and we do it face to face, but this will be later as mentioned. Hello everyone from myself also. I'm Manos Zapartas. I'm currently at the University of Geneva, and I will talk to you about the death of massive stars in binary systems. And here we see a death from a weird reason, from a dragon here in a binary system. First, let's start step by step. Massive stars are important celestial objects. Although they are very, very rare, they dominate the light of their stellar population because of their extreme luminosities. And maybe you remember from your stellar evolution courses that they are able to fuse hydrogen into heavier elements going up to iron in a very short time scale of a few or tens of mega years, so very quickly. And as they cannot fuse in elements more heavy than iron, in the end, they cannot overcome their own gravity, and their inner core is going to collapse almost instantly, producing such an amount of energy that it will result in a tremendous explosion called core collapse supernova. And these are very important events in many fields in astrophysics, because they enrich their surrounding environments with heavy elements. This is pretty much one of the main reasons that we can say that we are made out of stardust. And they also shape and drive the evolution of their host region, because of their mechanical and radiative feedback to their environment. Now, the canonical picture is that there is a minimum initial mass threshold around 8 solar masses. It's a little bit uncertain, but it's around 8 solar masses, above which the idea is all stars produce a core collapse supernova, whereas below that threshold, stars form white dwarfs without an explosion. If we see the evolution of these massive stars in a Hertzsprung-Russell diagram, we see that stars from 8 to around 20 something solar masses evolve through their main sequence and then quickly expand a lot and become red supergiants. And they explode as red supergiants in this part of the HR diagram. Whereas stars above this threshold of around 20 something solar masses, for solar metallicity at least, they are so luminous and have so strong winds that they can expel their outer hydrogen-rich layers, and we are left with hot, compact core of heavy elements, which is observed as a Wolf-Rayet stars from observers. And if and when this explodes, the idea is that it will produce a hydrogen poor supernova. Not a lot of hydrogen will be seen in the spectra, and it will be in this part of the parameter space. So I kind of already mentioned the two main classes, observational classes for core collapse supernova, the ones that show hydrogen signatures and are supposed to be coming from progenitors that have hydrogen at the moment of explosion. They are also called type 2 supernova. And various classes of type 1 supernova where they don't show hydrogen in the spectra. So another important reason to study these massive stars is because after these, after their collapse and their supernova, they leave us a compact object remnant, either a neutron star or a black hole. And again, the canonical picture up to around a decade ago was that stars above, just above the threshold for a collapse would form a neutron star, whereas very massive stars will form a black hole. In recent studies in the last decade have shown that the picture is a little bit more complicated, and that whether a star will form a black hole or a neutron star is highly sensitive to the inner structure of the core at the moment of collapse. And various studies try to parameterize this. One of them tried to parameterize it with this compactness parameter, which is pretty much shown here. It's the mass and the radius of that mass coordinate pretty much kind of give us an idea of how compact the inner part of the core is. And the idea is that if this compactness parameter, which is here on the y-axis, is high, then the core is so dense that it cannot expel its outer layers at the moment of the collapse. So it collapses directly onto a black hole without an explosion. So this could mean even that we do not see any observable event from this one. So we have the implosion pretty much of a star onto a black hole without an observable event. And this already changes the picture from the idea that all massive stars produce an observable event. This is still on a theoretical perspective, but there have been candidates that where they see that this has happened. And then again, for lower compactness, the idea is that we have successful explosion in a neutron star production. And as we see, this compactness parameter is not a monotonic function with initial mass. So we may have parts of the parameters where we produce neutron stars, some other parts where we produce black holes, then again neutron stars. So it's a more complicated. Now, if we have these compact objects in binaries, they form a different, interesting group of systems. If we have a neutron star or a black hole accreting material from stellar companion, it forms a disk around it, which is so hot that it emits in X-rays, and it's called X-ray binaries. Whereas on the other hand, if it has another compact object companion, and if they're close enough, they may spiral in due to gravitational wave radiation, and they may even merge. And this has been detected in the last few years with laser interferometers like LIGO and Virgo. And this was an extremely important new discovery because it opened a new window to study these objects. I will focus on these systems a little bit later in my talk, but I want to note here that they are crucial for our understanding of the evolution of massive stars and of compact objects, because they're one main way to study them, and especially for stellar mass black holes, they are the only way to detect stellar mass black holes, because if we have just a black hole in isolation, we cannot even detect it. What I want to focus on right now is this keyword that I already mentioned, which is binaries. Here I talked about compact binaries with a compact object, but in reality, there have been many observations that showed that we expect many massive stars to be in binary systems already from their birth and interact with a companion from their birth. And in fact, if you want to keep one message from my talk, probably would be that it is expected observationally, and in some cases theoretically also, that most massive stars in one of these studies is shown that 70%, around 70% of O-type stars are expected to interact with a binary companion and exchange mass with it at some point during their lifetime. So when we're talking about binary evolution of massive stars, we should not think of it as an exception or as an exotic event. This is probably their normality in their evolution, and we need to take this into account when we study them. So here I want to show you an artistic impression of the evolution of two stars in a binary system. So we start with these two stars. In the beginning, they are effectively evolving as being in isolation, although tidal forces are already in place, so they may span up the star, and we may have internal mixing because of this. So already binarity plays a role. And what we're going to see is that at some point, the most massive star will expand first and will fill its Rosslow, which pretty much means that the gravity of the other star will start winning on the surface, and we will have mass transfer from one star to the other. And from now on, the evolution of both of these stars will be radically different after that. So what we're going to see is that the massive star will lose most or all of its hydrogen-rich envelope and becoming a stripped helium core. That's how we're going to call it, which will still collapse in a supernova, but it will be a hydrogen poor supernova because it does not have hydrogen layers on top. And then the other star will also keep evolving and will also produce its own, in this case, hydrogen-rich event. So the general question that I will try to address in some of the next slides would be how this binarity would affect this core collapse supernova. And one of the main ways to address this would be to use binary population synthesis tools, which in many cases when I use them, I use a specific code which is called binary C. And the idea in these binary population synthesis tools is that we are able to evolve a large population of single and binary systems of different masses, different orbital configuration, different metallicities. And then we evolve all of them, making some approximation in the stellar structures and take into account physical processes that may take place like stellar winds or mass transfer. And in the end, we can get information about the statistics of events or systems like core collapse supernova, or in other case, X-ray binaries or mergers of compact objects. So these kind of computational tools are a powerful tool to study the rates of these events, to study the trends in the distribution of the properties of these events, and also to show us which are the dominant channels that lead to these events. On the other hand, because we are, we need to have in mind that as we need to have rapid codes, we do some approximation and we have some uncertainties in this part of the evolution, maybe even in the initial in the initial distributions. which means that one usual thing that we're doing is to rerun this population with different assumptions to see how sensitive we are to this assumption. And the fact that we are getting information about the statistics of these is that we can use them as a theoretical framework to interpret and compare with the large amount of data that are coming nowadays for all these important events. And now here I'm showing just a few examples of surveys that are looking at core collapse supernovae or X-ray binaries or gravitational wave sources. And we start building high number of events to get statistic of the bulk of the population. Now I'm going back to the question of how does binarity affect core collapse supernovae. The most obvious way is the stripping of a star due to being in a binary. So we're gonna have that star losing its hydrogen envelope, and it's a stripped helium core, and when it's gonna explode, it will be a hydrogen poor supernova. So we already see that the canonical picture that I talked in the beginning changes because we can have stars in the mass range where we expected only red supergiants to be able to be stripped due to binary interaction, even though they wouldn't have strong enough winds to do this by themselves. And if we see this in the HR diagram, we see an expansion of the parameter space to lower luminosities and lower masses for the progenitor of this stripped envelope supernova. And so this blue and probably this yellow part of the parameter space. And this is consistent and may even at least partially explain the high rates of this hydrogen poor supernova, the low ejecta masses that is found in this supernova, because now we're talking about lower mass cores that explode, and also the difficulty to detect massive Wolf-Rayet stars as supernova progenitors in this supernova. And another thing that is also very interesting is that there have been studies of how the stripping of a star may even affect the explosion mechanism itself. I already mentioned before this compactness parameter, and there have been studies that are trying to see how these are affected from stripping a star. And what we see is that although for single stars above around 30 solar masses, we expect them to have to form a black hole in the end, potentially without a supernova. If the same star is stripped early in a binary system, it may end up forming a neutron star in a successful explosion. And this is partially due to the fact that it will make a smaller core because it was stripped and it will not be able to form such a big core. And partially because even for the same mass, it seems that it will have lower compactness parameter. Okay, so I already I talked about this star. Now I want to talk also about the other star, which is the mass gainer, the one that gained mass. And I want to combine it with the possibility of merging two stars in a binary system, where the two stars come close enough or are, because of unstable mass transfer, they end up merging in one another. And we are left with a highly spinning new single star now in isolation that will evolve and probably explode also in the end. And I'm putting these two together because in both of these cases, pretty much we have a star which gained mass either by mass accretion from a binary companion or with merging with a binary companion. And we expect that most of them will produce hydrogen-rich supernova now in this case. So we go to the other class of this supernova, and we try to quantify what is the expected fraction of type 2 hydrogen-rich supernova that we think that it's coming from binary products. And what we find for various assumptions in our population synthesis studies is that between 1/3 to half of type 2 supernova, we expect them to be coming from binary products. And that's a significant fraction, and we need to take this into account in our study. In fact, there have been solid arguments that the most famous and the most well-studied supernova, 1987A, in the nearby Large Magellanic Cloud, is probably a binary merger, because this can explain many of the peculiarities of this event, like its blue supergiant progenitor and potentially the rings that are seen around it. But we need to have in mind that we need to have in mind that if this picture is real, then we would expect many of the normal supernova to be coming from binary mergers. Now I want to go to another different probable consequence of binary interaction, which would be on the mass, on the expected core mass of pre-supernova or progenitor of this supernova. And what I'm showing here is simply that for single stars, for a given set of assumptions, like in convection or rotation, we expect that for higher initial masses to have a higher final core mass. Now, this one-to-one relation breaks when we're talking about binary products, but this is not happening in a random way. On average, we expect that for the same initial mass, we expect a higher core mass in the end. And this is simply because, as I'm trying to show in this hand wave example, if we have a 15 solar mass star in a binary, and it merges with, let's say, a 6 solar mass star and makes something like a 20 solar mass star now in isolation, when it's going to explode, it's going to remind more of this 20 solar mass core. And now, so I have to say that I've oversimplified a little bit here, because it's not that we can just add the masses and say this is a new single star. In reality, we expect the merger product to also be highly spinning and to induce mixing inside the new isolated object now. But on average, the picture that we're gonna end up on higher core masses will be there. And this is very important in cases of, in case we want to gain insight about this explosion, because I have to note that when we see an explosion far, far away, we don't really know which star exploded in this supernova. Pretty much we see the explosion, but we don't know what was the bomb. So one way to try to tackle this is to try to go to supernova that are in the nearby galaxies and try to see if we have an image of that region before the explosion. And maybe we can identify what star exploded in this supernova. So we make a link there. And what we are saying here is that if that star that exploded had this kind of binary evolution, maybe we will misinterpret that the explosion occurred from a single star of a 20 solar mass star, whereas it was a 15 solar mass in reality in a binary system. And we try to put this in the context of the red supergiant problem, which is the apparent lack of luminous red supergiants as progenitors of this supernova, this type 2 supernova. What I'm showing here is like a cumulative distribution of observation with this method that I just mentioned of nearby supernova, which show masses up to around 18 solar masses. And the black line is the theoretically expected one following an initial mass function, canonical X-Salpeter one. And this discrepancy here, the fact that we do not see anything happening from a luminous red supergiant, is considered to be the problem. Now, there are arguments that maybe this problem is not statistically significant. There are also other arguments that are trying to say that maybe we are looking exactly this part of the parameter space where the compactness parameter is high, you see above around 20 solar masses. So maybe these very luminous red supergiants are not producing observable events, but they are imploding in a black hole. What we wanted to study here is how would this picture change if we take into account binarity, that many of these explosions are coming from binary products. And what we've found with this red line and the whole red shaded region here for many variation in our assumptions is that binarity does not seem to help solving the red supergiant problem. In fact, it may make it slightly worse. And the reason for this is again that if we had a 15 solar mass star that merged and becomes something like a 20 solar mass star, we would expect to see an explosion from this 20 solar mass star, from many more 20 solar mass stars that gain mass. And we don't see them. So if the issue is still there, binarity probably will not solve it. Another implication of this binary interaction of these progenitors is that there are independent methods that are trying to gain insight about which star exploded. And instead of trying to figure out which star exploded, they are looking at the surrounding region around the supernova site. And in this way, they can put in a color magnitude diagram and they try to get an estimate of the age of this region, which will correspond to an initial mass of this supernova progenitor. What we argue here is that this method will probe more accurately the actual initial mass of a progenitor in a case of a binary system. So in this case, the 15 solar mass, because the nuclear timescale, the evolutionary timescale of this star is the one that will dominate the whole time for the evolution up to the supernova. Whereas, as we mentioned, other methods, including the direct pre-supernova imaging, they will probe the pre-supernova state of the progenitor. And we argue that there will be a systematic discrepancy between these two methods in the case of binary products. And this needs, first of all, to be taken into account when we try to interpret our results. But on top of this can be used as, we argue that this can be used as a way to try to identify candidates of binary products in this supernova. And I'm showing here the estimates of the masses from these two different methods. For single star progenitors, we would expect them to be in this one-to-one relation, but for binary products, they would be out of this relation. And if we show some observational data from supernova that have estimates from both of these methods, we see that there are a few that are on this regime that we expect, and we argue that these are potential candidates for these binary products. And I just want to mention also very quickly that this whole picture can also occur in stars that are below the threshold of the minimum mass for core collapse supernova. So in this example, we have a 6 and a 5 solar mass star. Normally this would make white dwarfs, but if they merge, they can make probably a 10 solar mass star that in the end will explode in a core collapse supernova. So we see that binarity may violate the canonical picture that says that we cannot have a core collapse explosion below this mass threshold. And we argue that these supernova from intermediate mass stars in binaries, they would have long delay times from their formation. They will be late core collapse supernova. They'll explode when all single stars have already exploded. And there are various observational evidence that this is occurring either on systems that seems to be progenitor of this late core collapse supernova. They seem to be already of long age, more than 50 mega years, for example. Like, for example, Phi Persei, or in systems where we have a white dwarf and a neutron star, where we believe that the neutron star was formed after the white dwarf. This is a reverse of the normal order that we expect. Or in case of studies that are probing the age in supernova remnants, and they are finding long delay times for core collapse supernova there. Okay, so here I want to make a slight change in my subject, and I want to present a new computational tool that we are developing, and briefly mention a few results from an early version of this tool in the context mostly of gravitational waves and X-ray binaries. So I already mentioned that rapid population synthesis are important to get the statistics of population like X-ray binaries and core collapse supernova. And here I'm showing most, I assume, or maybe even all of the rapid population synthesis codes that exist that you can find in the community. And I want to mention specifically BSC, which was the first in these seminal papers from Hurley et al. And pretty much all the rest are a slightly alternative version or an upgrade of this BSC code, usually focusing on more on specific field of studies. Now, all of these codes need to evolve a big amount, a large amount of population of binary systems. So they approximate the stellar structure by using either fitting formulae or tables to interpolate that are all based on pre-computed single star models. And sometimes these models may be 2 decades old. So we know that we lose most of the information of the inner structure of the star in this kind of codes. And we also know that we lose much of the accuracy in the stellar structure, especially when we're talking about stars that are during binary mass transfer, where we know that normally the star will be out of its thermal equilibrium. So in order to make an important step to tackle these issues, I'm part of collaboration where we want to, we develop a tool, a framework to do population synthesis studies using detailed binary stellar models. And this collaboration is called Population Synthesis with Dynamic Grids of Simulations, or else Poseidon. And the PIs are Tassos Fragos in the University of Geneva here, and Vicky Calogera in Northwestern University in Chicago. And we aim to have something public and open at 2021. And in fact, Konstantinos Kovlakas, who's there in Iraklio, is also one of the core developers in this code. So the main idea here is that we want to combine large grids of binary detailed models with coupling it with algorithms that can handle physical processes that are difficult to handle with stellar evolution codes, like the collapse, the kicks, and a common evolution. The main advantage from this approach is that we have information of the internal structure of the stars in these binary models. We take into account rotation and potential differential rotation in the structure, mixing inside the stars and tidal effects. And we can calculate the stability of mass transfer, whether it's going to be stable mass transfer or it will go to an unstable, probably following a common envelope event. From these models themselves, not using assumptions from previous studies. Now, of course, as a compensation, because this is computationally more expensive, it means that we lose some of the flexibility that rapid population synthesis codes have in rerunning these populations with different assumptions during mass transfer, for example. And I want to show a few results from early versions of this code where in this context, we're talking about gravitational waves and specifically about binary black hole mergers. So going again to these events, in order to have binary black holes merging, we need to bring two black holes in a very close orbit of tens of solar radii at most. And this is difficult in nature because we expect that the progenitor of these black holes to be much bigger than the orbit that we try to fit them in. So we have to figure out how this occurs. One group of ways that we think this occurs is that if these black holes are formed in a dense stellar environment, we are able to bring them together through dynamical interaction, and then they can merge within a Hubble time. Or we are already starting with a binary system, and through different binary scenarios, we may end up with the two black holes in a very close orbit. And in a study led by PhD student Simone Bavera here in University of Geneva, he focused on two scenarios, the common envelope scenario and the stable mass transfer. And the idea there is that we have mass transfer between the two stars, and we have various cases of mass transfer. And in the end, we end up with a black hole of a negligible spin next to a helium core, which will make the second black hole, the second Bohr black hole. And at this point, we change from a rapid population synthesis that I was talking earlier to mesa binary detailed models. And this is because we really want to probe and investigate how tidal forces will affect the inner structure and the spin up of this helium core, and whether the second Bohr black hole may be of high spin or not. And the main conclusion is that after the common envelope scenario, we may end up with orbits that are tight enough to spin up the black hole, whereas in the stable mass transfer scenario, the orbit is not so close, and the second Bohr black hole probably will also be of negligible spin. And why do we care about this? We care because two of the main observational constraints from LIGO Virgo detection of binary black hole mergers are, one is the chirp mass, which is a combination of the masses of the two black holes. And the other is this chi-effective parameter, which is the projection of the mass-weighted average of the spins of the two black holes on the orbital angular momentum axis. Pretty much it tells us something about the spins of the two black holes. And we show these two quantities in this graph. And what we see is that we expect from these scenarios that I mentioned that most of them will have a chi-effective around 0 because both black holes are of negligible spin. But we also find a tail of positive chi-effective. And Simone has worked on this subject a lot. And on top of this, we can also see the detections from LIGO-Virgo collaboration, including the events that became public a few weeks ago. And some of them are consistent with these models. There are a few that are not easily consistent, mostly the ones that are of high chirp masses. We can discuss about this too. But what I want to mention here is that I think this is a very good example where we need to combine the strength of a population synthesis work to get rates and to get distributions, and at the same time to have high enough accuracy to probe the internal structure of the stars in order to get accurate estimates of the spin of the final objects. And in just on the remaining few minutes, I just want to mention a second example in the context of black hole wind-fed X-ray binaries. The idea in these systems is that we have a black hole which has an accretion disk around it, fed by the wind of a massive star in a closed orbit. And there are 3 confirmed detected systems of this kind, with the most famous one probably being Cygnus X1. And we're trying to reproduce some of the observables of these systems, including their X-ray luminosity, the masses of the 2 stars, and the spins and the orbit of these systems. And in order to achieve this, we again have a similar train of way of thinking where we have now binary simulations up to collapse, not rapid simulations. And then we let one star collapse take into account a prescription about the mass of the remnant, about potential loss of mass due to a very highly spinning core, and readjusting the orbit in a new eccentric orbit after a potential kick of the black hole. And then we couple we match now the donor star to single star tracks from MIST, which are also based on MESA, and evolve the eccentric binary orbit now in order to get this phase, which would be the black hole wind-fed X-ray binary phase. And we focus on this scenario where we already start from close orbits, because we want to see if it's possible to reproduce the high spin of the black hole, which is seen in all 3 observed systems that I talked earlier. Now, this is work in progress. I'm showing here pretty much a complicated plot with all the observation constraints that I'm mentioning. There's a lot of information here. I don't want to go into details of that one. One thing that maybe I want to mention is that we are able to reproduce the high spin of the black holes, but only if we assume inefficient inefficient angular momentum transport inside the stars. This is one of the uncertainties both in single and binary evolution. And this has been shown, this is consistent with previous studies on the same subjects. One of the steps that I'm working on right now is to try to see if the highly spinning black hole could be related using this tool now, like to try to quantify whether this could be related with long gamma ray burst, which is another type of event, that explosive events that I did not talk a lot about, but it is highly related with a highly spinning core that collapses onto a black hole. And again, I think this is, like, I don't want to go into the details on that one, but again, I think this is a good example where we would need a combination of being able to run many systems, but also keeping enough information so that we know, we have insight of the internal structure of the star at the moment of collapse. So I'm showing my summary here. And very quickly, just to mention again that I hope that I convinced you that binarity affects the life of massive stars, which are the progenitors of core collapse supernova and of compact objects. It can increase the number of stripped envelope supernova, and it can change the part of the parameter space where we expect them, potentially change their explosion mechanism. It can also produce hydrogen-rich supernova with higher core masses unexpected in isolation, and even violate the minimum mass threshold for this explosion. And I've also presented you and show briefly some results from a new population synthesis framework that we're developing using MESA binary detailed simulations. Thank you very much.
Thank you very much, Mano, for this very interesting talk. Do we have any questions? I do see some questions on the chat. So, and I see a question from Andrea. So why don't we hear Andreas first, and then I can read questions from the chat if you'd like. Andrea.
Thank you, Vaso. Thank you, Manos. That was a very, very interesting talk, very interesting results. So I have two questions, one for the first part of your talk and one for the second. So regarding the supernova time delay function, have you tried to compare this with measurements of the time delay function in the Magellanic Clouds, for example, from the work of Dan Maus and Carlos Badenes, where they try to measure the time delay of the supernova with respect to the local stellar populations, and to see whether you see this extension to older timescales. That's one thing. And the other thing is, what do you think about comparing the time delay function for hydrogen poor and hydrogen rich supernovae in order to test the two scenarios?
Yep. Should I answer this first?
Yeah, then we can go to the next one because it's different subject.
Let me maybe go back to this one. So in fact, maybe I have a backup slide, but it's very far away. So in fact, we have done exactly what you've mentioned, and Carlos Badenes is also a co-author in this work.
All right.
We pretty much in the Large Magellanic Clouds, we use the supernova remnants there, trying to, and they are mentioning pretty much that they have found a signal which is coming at around 100 and 200 mega years. They expected that these are type 1a supernova, because from single star evolution, you don't expect anything from a core collapse here. And they even if we can mention this, there is some uncertainty, but they are finding even an excess there, where we're saying, oh, maybe there is an excess in type 1a. And now we're saying that, no, maybe they are not early type 1a supernova, they are late core collapse supernova. So there are some work towards this direction. Of course, it's not so easy to really pinpoint an age for all of them. And the other thing is, I don't have the figure here, but I can already mention here, I'm showing all core collapse supernova. In reality, even from single star evolution, we would expect type 1 supernova to explode first and type 2 supernova to explode later. And there will be a cutoff between the two. Whereas with binary evolution, we would expect type 1 supernova to have a tail, even in longer delay times, and type 2 supernova to spread also, but still, on average, we would expect that type 1 will come first. So with studies that probe an average trend, the trend will still be the same. Now, if we're talking about specific events, and if we can find accurate enough age estimations, then maybe we can say something about a binary product.
Okay, thank you. That was so. Effectively, if you had accurate ages, then you could look for the gap that you would expect from single star evolution, and if you don't see it, then that would be evidence for binary evolution.
Yeah, in a way, yes, I think so. Although I think we don't have so much accurate estimates that we can clearly say this.
Yes, if we had, yes.
Just that. So this is a trend that is coming from binarity. In reality, there are effects that are coming from uncertainties in single star evolution also for different convective cores, for different metallicity winds, for different rotation rates. Time scale are also changing. So we need to have this also into account.
Okay. And so I don't monopolize the discussion. Let me go to my second question. So this has to do with the chirp mass versus chi effective plot that you showed. And there was an island in the, as you mentioned, to higher chi effective values, but there are no observations there. Is this observational bias because these are in low mass objects? So the current detectors are not sensitive, or there's something else going on?
So here we already take into account we're trying to compare apples to apples. So we already take into account the sensitivity of LIGO Virgo to higher chirp masses. So the reason that we see this tail being in low chirp masses is pretty much because lower helium stars can fit in closer orbits. So it's easier to spin them up, much more than massive helium stars. So it's true that we don't see observations exactly on this island, but I would still say that from a point of view, from a statistical point of view, this is still all of these systems are consistent from this channel, still showing that a few of these events are not easy to be coming from these specific channels on that one.
Okay. Okay. So, but I guess the picture will be clarified with the next runs. So we'll have higher sensitivity and more events. So we can try, we can see how this diagram is populated.
Yeah.
Yeah. Okay.
Do we have any other questions by microphone for Manos before we go on to the questions on the chat? Okay, if not, I can read a few. So one question refers to something that you mentioned earlier in your talk, the compactness parameter. And the question is whether this refers to a core that is not yet degenerate?
So it refers to the pre-supernova core at that point. So
yeah, I understand. This is Vasilis. Hi, Mano. I was just wondering, right? Because if you depending on how the evolution goes, right? I assume since these are massive stars, the helium core never goes degenerate, right?
yes, that's true. And so what I wanted to mention on the pre-supernova core, pretty much I'm saying that they are really mentioning that this parameter needs to be calculated exactly at the moment that we have the collapse, because they are trying to probe the entropy of the inner core at the moment of collapse. And this will say whether we're going to have enough neutrino luminosity to be able to unbind the whole core. So yeah, we are talking about really the part that is not it's massive, but it's not degenerate there on that.
And this is the reason why it can get so high mass to begin with, right? The core itself can be fairly massive then, the helium core.
Yeah. It can be like we expect to have CO core masses that collapse of more even than 10
right.
solar mass, 15 solar masses, and this is not in conflict with the Chandrasekhar mass.
Yeah.
That's what I'm saying, because we're not in this degeneration.
Okay, thank you.
Okay, so next question is, what happens to the cores of the merging stars? Is there an interruption of the fusion?
So again, first of all, it is uncertain. It's very difficult to model merging objects. There are many uncertainties on what's going on there. In general, we would expect that we're going to have an isolated object that will be highly spinning, and that it will mix a lot. And mix a lot means also potentially bring new fuel inside the core to burn. This is a process that in general is called rejuvenation, where by having binary interaction, we bring new fuel, hydrogen fuel in the core, which will be burned. So we go back in the age of this star. It has now more time. Studies that have tried to see the short-term and the long-term evolution of these systems have shown that in the beginning, we are out of equilibrium until we settle again. This may be also shown as a puffed up star out of thermal equilibrium. And we may have this mixing in the core, but this will settle quite, I think, quite fast again. So in the long term, we will still have isolated mass that will continue its evolution towards the collapse.
Thank you for the answer, Leon. Was my question. And what happens if one star already has a fusion in layers, in the outer layers, around the helium core? If there are fusions of hydrogen and when there's a merging, what can happen?
So again, I'm not 100% sure if we know how the fusion will continue in the very just after the merging, but in a fast time scale after that, when we are still going back to a equilibrium state, we will have a new structure where we're gonna have again the cell burning and the cone burning there. I have to mention that the uncertainty is high enough that in sub-studies, so when we have two stars merging, it's not exactly clear which parts of each star will end up in the final object. And there has been some studies that show that the ones that have the that are the denser or have the lowest entropy will end up in the core of the new single star, with all the uncertainties that are coming from hydrosimulation that are so much complicated.
So actually, we cannot track a kind of this star on the HR diagram. It's very hard how it will evolve.
There have been some studies on that one. I don't have a figure on that one, but there have been some studies of how to track them. But this would be a quick evolution in the HR diagram, and at some point they will settle again.
Okay, so next question is, do you think high Gouffre or pre-supernova spins in general are necessarily correlated to the high black hole spins? And couldn't you lose a lot or most of angular momentum in some ejected mass or in a disk?
Yeah, that's exactly the case, pretty much, and that's the reason that for the studies that I mentioned in the end, even if we have a highly spinning star close to the collapse, if we have strong winds, especially Gouffre winds, we may lose this angular momentum before the collapse. And that's where the angular momentum transport inside the star plays a very important role, because in case the envelope is not highly coupled with the core, we may be able to, even though the envelope will spin down, the core maybe will still be highly spinning. But if they are highly coupled, and if we still have these strong enough winds, we need to find a way to keep the core spinning, although we are draining it from its angular momentum. Maybe tides play a role there to keep it spinning, or if we spin the core late enough in the evolution that it does not have time to spin down until explosion, this could be a way to retain angular momentum up to the explosion.
Hi, Manos. It's Alejandro. That was my question, and thank you for the talk and for the very nice answer. I was talking about even a more extreme version of it. I was talking about, let's assume that you have a low metallicity, so you don't lose the angular momentum, and you have tides, and you're almost at core collapse, still very efficiently transporting angular momentum. Could it be that you can get rid of angular momentum just in the final stages of the collapse? Is this something that maybe by getting everything out through the outer layers and then just expelling a little bit of it?
Are you talking specifically at the moment of the collapse also?
Yes.
Okay. So this is something that we also try to take into account as self-consistent as possible. So there has been work from Aldo Bata et al., where pretty much at the moment of the collapse, we take into account the angular momentum profile of the collapsing core. And instead of letting all the mass falling inside the core, we see whether it can make an instantaneous, whether it can form an instantaneous disk with angular momentum more than the ISCO of the forming black hole, pretty much. And part of it will be expected to be lost and not end up in the black hole, potentially forming jets. And this is pretty much the collapsar idea, collapsar scenario for a long GRB also, if this is a strong enough event. And we try to take this into account in the Poseidon framework, where we keep track of the profile of the star at the moment of the collapse.
Thank you very much, Manos. That was very nice.
Thank you.
Okay, I saw another microphone turning on. Do we have another question by Mike? Okay, if not, we have a few more questions, but a little time. So let's try to at least go over them, have some short answers. One question is, could you say a little bit more about the kick in the collapse phase, what exactly it is and how you model it?
Yeah. So in general, when we have the collapse of a star in a binary system, if we lose a mass, this will import some kick just by instantaneously losing some mass from one star. Apart from this, the idea is that if there are ejections of mass or neutrinos that are not isotropic, so if we have anisotropies in the collapse itself, we may end up with an innate kick of the compact object. And this, in most of the cases, when we form a neutron star, will disrupt the system. So we follow a Maxwellian distribution of 260 kilometers per second for neutron star collapse. This is pretty much what is mostly used in most population synthesis code. For the black hole kicks, we know it much less. There are some arguments that for black holes, because for black holes, the kick should be lower, although this is a debate in reality. So a good thing that we can do with both with rapid population synthesis, but also in Poseidon framework, for example, is that we can rerun our simulations with different assumptions in the kicks, especially in the black hole kicks, to see how sensitive our results are on this kick. In the results that I've shown at that point, for the X-ray binaries at least, I assumed lower kicks for black holes in case that we have fallback of material, where we expel some mass, but they still go in.
Yeah, thank you very much. I was just wondering exactly, because we usually see kicks in the core collapse supernova simulations, but to my knowledge, there is no clear message, like if we have a higher mass progenitor or lower mass or angular moment, what role does this play to a kick? So I was just wondering if you take all this behind physics into account, but yeah, do you have like any reference to point at, or?
Yeah, so the ones that are being using in population synthesis, this is mostly from Hobbs et al., which is observation of pulsars. But again, this is an uncertain field, but I would probably point most to Snyder et al. 2020. I can show the ones I'm saying. To this one here, where they're trying to figure out if stripping of a star would change the energetic of the supernova, potentially the kicks of this supernova, and how this situation changes in case of binary interaction before the explosion.
Mm-hmm. Thanks a lot.
You're welcome.
Okay, so next question is, how does the second star survive from the explosion of the first star?
Right. So this is, I think this is an intuition that most people have. I had it also in the beginning. I thought that one star would just be destroyed from the explosion or from the first explosion. This is not the case. So keep in mind that this is much more compact than the ejecta, the supernova ejecta that will hit it. Still, there are studies to try to investigate exactly what is the outcome of the supernova ejecta hitting that star. And they find that it will impact some velocity to it, and it will also pollute it with some chemical material from the supernova ejecta. And at the same time, it will strip it a little bit on its surface. So these are some signatures that are important, but from an evolutionary point of view, this will not change the evolution of the star next to it. which in most of the cases anyway would be a compact main sequence unevolved star at this point in the evolution. Or not very much evolved star.
Okay, thank you. And we have one last question, which is, you mentioned that you have to assume inefficient angular momentum accretion to reproduce the spins of X-ray binaries, right? And how does that affect the predicted spins of neutron stars and white dwarfs?
Right, so there is a lot of debate on the angular momentum inside the stars. I have not studied, so I'm not so comfortable of remembering how it would affect that of neutron star or white dwarfs. I remember that the general case is that from work from Fuller et al. And work in groups in the University of Geneva also, is that we expect probably to have an efficient angular momentum transport in nature. So the fact that we assumed an inefficient one, it's not an argument to say that we found that that's the case. We are playing this game to try to see how could we reproduce the highly spin in high mass X-ray binaries. And if we reproduce it in one way or the other, what can we say of potential having a collapsar models in many of them, but not of really saying much about the physics of the angular momentum transport on that one. We can see how much we would need in order to try to reproduce it. Because if we cannot reproduce it, then this would be still a question that we see it in nature, we see it in Cygnus X1, and we need to find out how this black hole is highly spinning.
Okay, thank you, Mano. And since there appear to be no more questions and given the advanced time, let's all thank Mano once again very, very much for this interesting and very interactive talk. And we're very much looking forward to a repeat performance in person once the pandemic is over. Thank you, and thank you everybody for coming.
Thank you for your invitation. Thank you, everybody.